Hello, this is Owen Prysock, and this is my Lab 4 lab report on bar magnets. So in this experiment, we measure how the field strength of a bar magnet changes with respect to both position and distance away from the bar magnet. We then use certain computational models like the Biot-Savart law to calculate the magnetic dipole. From there, we calculate the net magnetic field at all these different observation locations from the magnet. And the overarching theme of this whole experiment is that bar magnets have this dipole-like magnetic field structure with a dipole moment that stretches from the South Pole to the North Pole, as you see in this picture to the right. Our experimental setup. So every phone has this magnetometer in it, and we did certain experiments and certain measurements to calculate where that magnetometer is. And for my phone, it is in the very bottom left, so this picture isn't completely accurate. But from there, we had two different ways that we determined the net magnetic field. And this one way in the bottom left, we only looked at the horizontal contribution of the magnet. And then in this top left up here, we calculated both the horizontal and vertical contribution due to a known distance from the magnet. And another note I want to add is that we lined up our phone and the bar magnet perpendicular to Earth's magnetic field to mitigate any type of error in our measurements. And so here's our data. Um, there's a lot of different points, and I'm not going to go into those, but the overarching theme is that we're plotting the magnetic field um, on this y-axis due to position on this x-axis, and there's this negative correlation because the farther you are from a magnet, the less strength the magnetic field has. And it's very important to note this y-intercept right here, this negative 15.2. That'll come in handy later. But let's talk about the Biot-Savart law. And so originally, we see in the top right up here, it was used to calculate the magnetic field due to currents in a wire. Um, but a bar magnet acts like a dipole. And we know also that a small continuous current loop also acts as a dipole. So we can use the Biot-Savart law to help us out here. And so we rearranged the equation into this setup right here. And in this way, the bar magnet can be represented as this dipole with the U representing both its strength and orientation. And so here's our calculations. I'm not going to get into all of this, but we basically used the intercept from the Excel graph, which was negative 15.2, plugged it into our model that we see right here. And we get that the dipole is 1.25 amps per meter squared. So we plugged in our equation, our full equation, which is this right here, into the coding at different observation locations and calculated the magnetic field. And as we see here, all these different arrows and the magnitudes of the arrows resemble a dipole. And you can look at all of the magnitudes and axes here. But the main overarching theme, again, is that a magnetic field due to a bar magnet resembles the electric field from a charged dipole. And so if we hadn't oriented um, our experiment or phone to compensate for the magnetic north and south of the magnetic field of the Earth, how would our results change? Well, we wouldn't only be measuring the magnetic field due to the bar magnet, we would also be measuring the magnetic field due to the Earth. And so our results would be off and our magnetic dipole would be wrong. Another question is if we were to stick two identical magnets together end to end and run the experiment again, how would we expect our measurements to differ? So two magnets end to end, almost in like a series, they act like a battery in series. Our magnetic moment would double since the strength of the field doubles, and since our magnetic field is proportional to our magnetic dipole, we would expect the magnetic field to roughly double as well. Thank you for watching.